As well, it's 5 minutes past 2, so it's an honor to have Serena Curzel here with us at BSc. Serena is coming from Politecnico di Milano. She's a lecturer there. Hopefully, she will become tenure track or permanent position soon, we hope. And basically, Serena did a PhD at Politecnico di Milano. She was collaborating with PNL, with some friends from us also, Torino and Tomeo. And she will be talking today about HLS acceleration, which is a very cool topic.
Thank you.
Please go ahead.
So in this presentation, I tried to summarize some topics of research in my lab from the last 4 or 5 years. And they all are based on open source high-level synthesis, because we are developing and maintaining an open source HLS tool, and that allows us to do things that people cannot do with commercial black box tools. So I have these slides. They are divided into topics, and I thought because they are kind of standalone, then maybe we can do questions after each of them instead of at the end. We will see how it goes. So first off, we'll start by introducing this tool, which is called Bambu HLS. If you've never heard of high-level synthesis, it's a technique that allows people to accelerate applications on FPGA or ASIC, even if they don't have knowledge in writing low-level register transfer level code. So instead of writing in Verilog or VHDL, the specification for your accelerator, you can use a software description language, which is mostly C or C++, although we will see that this has changed in the last years. And the translation to Verilog or VHDL is done automatically. So it's sometimes we refer to this thing as hardware compilation, because it's the same concept. We are taking something at a higher level of abstraction and compiling it into a representation at a lower level of abstraction that does the same thing. So this means that theoretically, software developers or domain experts that have no hardware design expertise can achieve in a very short time frame some form of acceleration targeting either FPGA or ASIC. There are commercial tools out there. Many of the FPGA vendors have their own high-level synthesis tool that they distribute in their EDA suite. And there's also something for ASIC. One thing about our tool, Bambu, is that it can target both. It has been developed and maintained for at least 15 years in our research group, which is called Panda, and it is fully open source, available on GitHub. So this is a diagram with the internals of Bambu, which details a bit all of the compiler passes that are applied during the synthesis flow. So there's a front end where mostly the input gets compiled and optimized at the level of the compiler intermediate representation. And then we have the 3 core steps of the HLS process, which are allocation of resources, scheduling of operations, so we assign each instruction in the IR to a clock cycle and to a resource, and then binding the operations to the resources. After all of this, in the back end, we generate a synthesizable RTL representation of this. And the architectural model that's used is there's going to be a finite state machine and a data path, so the finite state machine dictates at each clock cycle which operations need to be done in the data path. Talking about the inputs that are supported by Bambu to describe your application are C, C++, and LLVMIR. This is done through front-end compilers that are standard GCC or Clang versions. We support many of them. We have almost complete support for anything you can write in C or C++, except for things that don't make sense on hardware, like you cannot have recursion with unbounded depth, because like once you fix the hardware, there it is, you cannot add more hardware resources at runtime. For the same reason, you cannot dynamically allocate more memory in your application. That doesn't make sense in hardware. But apart from this, basically, you can write anything in it. If you have STL-like structure in C++, if you have STL in C++, you can just replace them with the ETL, the embedded template library, that can be synthesized. And we have the support for the typical fixed point types that are used in most HLS tools. We also have some compatibility with the pragmas used in Vivado or Vitis HLS, the tool by AMD Xilinx. So a design that has been developed for Vitis HLS should be synthesizable with Bambu with minimal modification. So one input is the description of the algorithm to be accelerated. Then we have a lot of optimization directives that can be expressed through pragmas or command line options. And you can also add some constraints on the amount of resources to be used or the clock period, the target clock period. And then another important thing that can be considered an input to Bambu, although it is part of the tool, it is shipped with the tool, is a library of functional units, a library of IPs, which are characterized for each target that Bambu supports, which means that for each adder or functional unit that you have in the IP library, you know when you will synthesize that for a certain FPGA, how many cycles and how many lookup tables it takes, and if you want a different FPGA, how many cycles and how many lookup tables it takes. And this is crucial because this kind of performance estimation at the level of the functional unit allows for more optimized scheduling decisions. So the introduction of a new target for Bambu, a new FPGA, for example, is usually as simple as taking this IP library and synthesizing everything that's in there for the new target and gathering all the records from those syntheses and put them in the database. And in that way, you will be able to generate Verilog that is specialized for a new target. Outputs, synthesizable Verilog or VHDL, this can be chosen, target specific through this customization process. We currently have a bunch of FPGA targets available from AMD Xilinx. I think this is the most represented one in the database. But we also have Intel Altera FPGAs, and then FPGAs from Lattice and NanoExplore, which is interesting because Lattice and NanoExplore do not have a high-level synthesis tool, so the only way of targeting them is through Bambu. And then we have an initial support for ASIC targets through OpenRoad. So we did some experiments with the NAND 45 technology and the ASAP 7nm technology. Then you also get, together with your output Verilog, you get some scripts and other utilities automatically generated for simulation and logic synthesis and implementation. So for logic synthesis and implementation, Bambu automatically builds the scripts that are used to call the downstream, the backend logic synthesis tools, Vivado, Quartus, Diamond, depending on what is your target. So you can also never manually enter into this. You can just say to Bambu, after you created the Verilog, launch the synthesis script, and in that way you get the accurate measurements for the shift clock period and for the resources, the use of resources. And then we have this way of doing RTL simulation, which can be done with Verilator, ModelSim, or XSim. And we have the automatically generated scripts, but also, more importantly, automatically generated test benches, and I will talk about this in some later slides. We have, yes?
Can we ask, or
sure.
wait, you go back?
I can go forward, but not back, apparently. Okay.
No, I was going to ask for the ASIC. There are two things. We have been using in the past HLS from Xilinx and also from Siemens, Catapult HLS. We saw very different performance in terms of timing and area when using Catapult, much worse than this.
Yeah.
So I don't know if you have experienced the same, and what is Bambu? Is between the two of them, or? So
this is a very good question, and it's a fair question that everybody asks. We have not published up to now any benchmarking results because the academic licensing of these tools don't allow that.
You're not allowed. No.
But we're thinking of a way of pulling out some results that are meaningful and people can connect the dots and see what we're talking about. We would say, this is Bambu, this is tool X, very famous HLS. Industrial. Yeah, exactly. In general, what I can say is that it depends on the benchmark, but the one I'm most familiar with is the AMD exciting tool.
Mhm.
We are, on average, we get the same results, better on floating point and slightly worse on fixed point, because we have a very optimized library of floating point operators that they don't have.
Okay.
With Catapult, I don't know.
Okay. No, Catapult, in our experience, was much worse than
Okay. But actually, so because we're thinking about this benchmarking effort, if you have some like reference kernels that would help you understand where the performance is, we can take that into consideration. Because we were thinking of the regular like MaxSuite and Polybench, but if there's something more specific.
There is a new one this year. It's called Hetero. I don't remember the.
Okay.
But it's I started to see this year or something like that. I can pass it over.
Okay. Yeah.
I have another question.
Yeah.
So for the Verilog that you obtain,
Mm-hmm.
do you use fancy things from Verilog like structs and this kind of thing?
I don't know. What do you mean by fancy?
Like if it's just regular wires or
It's behavioral, very long, and I think it's all pretty straightforward. Yeah.
Because like sometimes the interfaces, I think with input and output and clock, and I believe we had some problems where clocking does not work with them.
Okay.
Just like kind sort of like system variable features.
Okay. No, so in terms of interfaces, we support the standard ones, like mostly AX by master to work with
no, interfaces in Verilog.
In there, okay.
System Verilog as an interface.
Okay. No, I don't think so. Because I don't think anyone has really touched the backend lately, so it's probably still there from maybe not 15 years ago, but.
And as a clarification, do you use like modular outputs for the Verilogs, or like is it usually?
It's not a blob, it's hierarchical.
Oh, okay.
Yeah, I mean, I wouldn't say it's like human readable, it's still auto-generated, but you can make out the hierarchy, yes, that's visible.
And the names?
Uh,
The names of the variables for
Yeah.
inputs and outputs are maintained at least.
so they're not completely random, but it takes a while to decipher them. Yeah. Another thing that we were thinking about was that it would be nice to have some kind of back tracing of these names and say, okay, this wire comes from this variable in the C. Haven't done that yet, but it should be possible. And yeah, as I say, there was, this is our reference paper where we presented the tool, like the latest one. And we have done some work in the previous years to create some Jupyter notebooks that can be run on Google Colab, just downloading a pre-compiled version of Bambu and trying it out. And there's some kind of small examples about the features that you can use. Although we do know that the documentation could use some more work. Especially because if you run the help, you have hundreds of options. That's not a way to describe what your tool can do, just running the help and reading everything. So, yeah, anything else about Bambu in general? Otherwise, we can go to Bambu and MLIR. So, I mentioned that one of the possible inputs to Bambu is an LLVM-IR, which opens the way for any front-end compiler that can generate an LLVM-IR to then target Bambu synthesis. So when MLIR was presented in multi-library 3D representation, we immediately saw that there was an opportunity because all of the high-level frameworks using MLIR, they could produce something that can be lowered to an LLVM-IR and synthesized. And this, the first cases were AI frameworks. And so we had experiments and this idea of creating an MLIR front-end for Bambu. So we didn't touch anything in Bambu in this case, but we created this MLIR front-end with the idea that we could use this to interface with the AI frameworks and then run analysis, exploration, optimization passes, all in MLIR to pre-optimize what we were going to synthesize later. And this was done when I was an intern at Pacific Northwest National Lab, and it resulted in what we call the SODA synthesizer. And so the synthesizer is a modular, multi-level open source hardware compiler, which is what I told you yesterday, so the previous slide. So Bambu as a backend and an MLIR front end doing all the compiler-based optimizations before synthesis. This front end is called SOLOpt, and there was the idea also of integrating a design space exploration tool, which was actually released. It's really simple in the current iteration. It just exploits the fact that we have the Python interfaces of the MLIR compiler, and so this little engine tries out some different combinations and sees what are the results in terms of timing from in terms of number of cycles from the simulation of Bambu generated accelerators. And in this front-end SOLOpt, it would stand for Search, Outline, Dispatch, Accelerate, because together with the optimizations, another thing that it does is it identifies the kernels to be accelerated, outlines them, sends them to Bambu, and then everything else in the application becomes the host application that talks to the accelerator. So we would have, at this point here, isolate kernel and host code. The MLIR kernel code gets optimized and synthesized through Bambu, and the MLIR host code has the calls to a kind of driver inserted into that and becomes the host executable. The optimizations that SOLOpt does for hardware generation are kind of standard transformations to extract data and instruction level parallelism. There's a lot of loop unrolling in here. There's some alias analysis so that Bambu can do more aggressive optimizations on the memory accesses, and so on. In general, at this stage, at the beginning, we only introduced in MLIR the passes for the identification of the kernels and the outlining. Everything else was already available, especially in the affine MLIR dialect. But then we also started introducing something else that we implemented in the front end. This is an example of what we could do with SODA. So we took a simple convolutional neural network trained in TensorFlow, and then lowered that through all the MLIR dialects, and then synthesized that with Bambu. And we could generate these accelerators targeting ASICs. This is, I think, the 9845 version. And we could see a baseline version with no optimization and a version with optimizations introduced by SODA, which would basically unroll a lot. In fact, the area gets much bigger, but this also means that the accelerators are much faster. And then we also have another example here. We did a similar thing targeting FPGAs, this time in the context of a European project that was aiming at better acceleration for FPGAs in space applications. So we have these non-explorer FPGAs that are developed here in Europe. They are specifically designed for aerospace because they have some tolerance to radiation built into the design. And we added the support for these FPGAs in Bambu, and we did the same thing. So we took a very simple CNN trained in TensorFlow Lite, in this case, quantized to 8 bits, and then synthesized it to one of these non-explorer FPGAs. The frequency seems incredibly low, 45.7 megahertz, but honestly, for this kind of space-grade FPGAs, it's not so bad. Like, even handwritten designs for these boards are not novel. Like, if you've ever worked in an aerospace projects, the hardware they use is like 15 years behind what you use at the ground level, let's say. And then, yes, I mentioned we also introduced something new in this MLIR compiler. One of these things is a set of passes for high-level loop pipelining. So the idea was that we didn't want to implement loop pipelining within Bambu. Back then it was not available. Now we kind of have initial support inside it. But loop pipelining inside the high-level synthesis tool is not trivial. While the idea was that we could apply a software loop pipelining in MLIR, generate a transformed loop, and then Bambu wouldn't know that the loop is pipelined, but the effect on the latency would be the same. And the second reason why I wanted to do this was with the idea that Bambu HLS at some point also open sourced front end that can be used to synthesize LLVM-IR. And so in theory, you could implement a transformation in MLIR, and that could be valid for both a Bambu backend and a Bambu HLS backend. I say in theory just because the performance that you get with the LLVM-IR front-end in Batis is so much worse than what you get by writing C, but it is technically feasible. And so the passes that we wrote were taking a loop in the affine dialect and generating a pipeline version of that loop by generating the body with each instruction coming from a different original iteration. So when this gets synthesized, it's synthesized as a regular loop, but because these three instructions are independent, they are scheduled in parallel, and the latency of the loop is the latency of the slowest of the operations, which corresponds to the initiation interval of the pipeline loop. Okay, so anything about the MLIR stuff?
So just to clarify, you said like code can be coming from like TensorFlow or like other pieces, right? And from what I know, TensorFlow, the code is written to write the kernels that will be launched, for example, on GPU or TPUs.
Yeah.
So you are saying that you will take maybe that kind of code, and when you compile it to MLIR, then to Bambu, you generate optimized hardware that can run those kernels.
Yes.
So you infer, because I thought that.
So there's so when you describe something in TensorFlow and then you ask the, I think it's called the compiler, I don't remember the name, you can generate the GPU code or CPU code. We take the CPU code version and we synthesize that one. Because when it generates GPU code, I think it already generates like the, I don't know if the binary or in with the instructions for the NVIDIA GPUs or something. So those are no use to us, but the MLIR version for CPU can get down to LLVM-IR and synthesized.
I see. So, but when the code is passed from C++, it is like actual description of the hardware?
No, there's no C++ in this code. That's the part. So when we use MLIR, there's no rewriting of C++.
I don't know, like I meant original Bambu.
The original Bambu?
The Bambu originally can have input as a C++.
No, but it can also have LLVM-IR. Like if you call Bambu and put something.ll as input, it will work. No matter where it comes from. This also opens the way to other front-end compilers. Like we have done, I think, half an attempt of doing Fortran, Clang, LLVM, and someone also did Rust compiler LLVM. This can be new areas of research.
Yeah, I think what I just got confused was that maybe I just know very less about HLS. So it's not like if it is not code written, let's say in Rust, even if it's a code written in Rust or C, that will later get translated to LLVM, right? Like, are they expected to be description of the hardware, but just in the high-level languages, or is it supposed to be an algorithm?
It's supposed to be an algorithm. Yes, you can describe the functionality that you want. Then the more you know about hardware, the more optimized results you get, because maybe you do memory accesses in a smarter way.
Yeah.
But in theory, you can just write functionality in your code and that will be translated.
Okay, it's just sort of like the best hardware that will suit that algorithm. Yeah.
So we have some experts at PSC that do LLVM with Fortran, auto vectorization and all of that, the compiler group. But I'm not sure if it would be easy to connect with that.
I don't know.
But maybe you want to talk to Roger. Maybe that's what.
Yeah, why not?
We'll take care.
Okay, then other topic, custom data formats. So I mentioned that we support the usual fixed point that people use in the head of the synthesis. but also that we have a very good floating point library, which is called TrueFloat. And it's interesting because it doesn't just give you single precision, double precision, but it gives you a fully customizable floating point representation. So you can have any number of bits for the exponents, any number of bits for the mantissa. You can choose a custom bias, and then there's all things that are in the IEEE standard that also can be tweaked, like if you want rounding or truncation, the exceptions, or maybe you don't care about the exceptions, so that will give you a bit of saving in area. You can support subnormals, hidden one, dynamic or static sign. So everything in this can be customized. The opportunities are that if you have fewer bits and you use a tailored format for your application, you could have improved quality of results because your functional units are faster, there's smaller logic. A smaller logic means that theory you could have more accelerators in parallel in the same area. There are a lot of challenges here. Mostly, you have to be able to assess the impact of this on accuracy. If you throw away half of your bits, will the results still be valid? The design methodologies, so there are libraries that allow you to play around with these formats in software, but then they cannot be synthesized. So this was also one of the reasons why we developed this library. And the biggest one, there is a wide design space to explore. So for now, it is up to the user to decide the format that they want, but it's not trivial to come up with a good configuration, good combination. So right now, this is how TrueFloat works. The users specify the required format. So for each function I have in my specification, I say how many bits I want for the exponent, how many for the mantissa, and if I want any more fancy customization on this format. And Bambu takes this specification and generates optimized arithmetic units for that. This is fully integrated within the HLS flow, which means that with respect to libraries that give you the floating point unit, you can get higher quality of results because you can optimize these together with the rest of the data path instead of just placing them there as a black box. And it's really easy to translate between different encodings. If you have different encodings in the accelerator, this is all handled automatically, and you can just change the command line option to try out many different configurations without ever touching your input code.
So how do you implement? So this is also in C++, and you convert it to system Verilog? And,
yes.
And then I guess it's only floating point. You cannot do bfloat or POSIX or other formats.
If you can, so bfloat, I think we can do it because bfloat can be expressed as a combination of exponent, mantissa, etc. POSIX, no, because it's a different encoding. So basically, what we have in the library is a C version.
Okay.
So, and then we have the conversions between float and custom format, and then we have the functional units implemented as just manipulations on bits and on integer numbers. Yeah, so you just take your input floating point function, add a command line option that says I want 6 bits on the exponent, 12 bits on the mantissa, and a bias of minus 63, and then the specialization string. And this in the within Bambu, the IR gets transformed into something that converts from the floating point inputs to the required data type, and then uses that data type to make the add operation. And the result is stored as an unsigned long int, because that's the smallest integer where this amount of bits fits, I think. Sometimes it works, sometimes it doesn't. Maybe the battery is gone.
Yeah, maybe the battery.
Okay. And I haven't got anything else here, but you'll see it later. Some research that we're doing right now with TrueFloat. As I said, the major challenge here is that we have the tool, but we don't know how to use it. So we'll have to provide users at some point with some kind of design space exploration to say, to see very easily what is the impact on accuracy and on quality of result of a certain choice in the floating point data format. Okay. Then Another line of research is about multi-threaded accelerators. This is recent, it's been done by a PhD student in our lab. It's called SPARTA, Synthesis of Parallel Multi-Threaded Accelerators. And a very brutal summary is it allows you to synthesize OpenMP code. The idea is that you describe something with OpenMP in your high-level representation, and we support parallel 4 sections of these data scope clauses and synchronization constructs. And then from this, Bambu generates an accelerator that has multiple cores that can execute concurrently. So in the final architecture, you have a lot of cores with local memory, and then you have some sequential computation that is the one outside of the parallel regions. And then there's a NOC that goes to external memory to allow all of these cores to access data independently. And then this is how it's done. It's integrated in the standard Bambu synthesis flow. We have a library of hardware components that replace calls to the OpenMP runtime. So when we have this input representation, we use Clang to translate that into an LLVM IR with the OpenMP runtime, and then we substitute the calls to the OpenMP runtime to calls through our functional units, basically. And then there's some more optimizations along the way that make this run smoothly. So this is your input. When it gets compiled, you have this fork call here, which has an argument OMP outlined. The OMP outlined function gets synthesized into a fork, and then multiple copies of this core are instantiated. And these cores can also be shared, meaning that if you have 16 threads, you may decide to only instantiate 4 cores and then do context switching on these 4 cores, which is useful if you have an irregular application that accesses memory, because the external memory access latency can cost a lot in terms of performance. So if a core does a memory access, the execution of that thread can be frozen, and you can use that core to do something else while the memory request comes back. So as I said, there's multiple parallel cores. We have hardware that takes care of arbitration and synchronization between them. We have implemented an efficient way of doing reductions, because this is a very common pattern in OpenMP programming. And you can also configure how many channels you have towards the external memory and how is the NOC built. And we've tested this on irregular applications on graph processing kernels, and it works very well. It scales very well. Yes?
How are the cores connected? Like, if they need to share some memory, do they have access to the same shared memory?
No, there's multiple levels of memory in the architecture. Like, this is simplified, but Bambu sees if something is only used by one core, it will go into local memory. If something used by multiple cores, but it's small, it stays on chip, but it is it can be accessed by all the cores. If it's used by multiple cores and it's too big to stay on chip, it goes to external memory.
So is there like L1 and 2, whatever?
Yeah. I mean, I wouldn't call them caches, but yeah, there's a hierarchy and multiple buses that.
Okay, so
yeah.
which is the architecture from core 1 to core n to access this memory? Is it like with a bus?
Yes. I have a picture, but it's not in the slides.
I can ask you.
Yeah.
So synchronization.
Yeah.
I'll just like to clarify first, cores here, is this like a CPU cores?
No, this is the thing. So with core, we mean a piece of hardware that has been synthesized from an OpenMP thread.
So it's like a kernel?
More like a kernel, maybe, yes. So the inside of this function is a core.
Oh, I see. And so like one parallel region can have like heterogeneous cores, or?
Yes, because maybe you have another Pragma OMP parallel later, and then you will have another set of cores that do different things.
Oh, but like in one region, it's always the same.
Yes. That's why we have like mostly parallel 4, also sections, but not tasks yet. We're working on that because this. Basically, we're exploiting the fact that every thread does the same thing except for like indexes. Otherwise, we cannot share the hardware. With this context switching thing, doesn't work if you actually have to use a different hardware. Like it would still be in parallel, but you cannot use also context switch on top of that.
And how do you configure this course from the outside? Like there is a CPU that talks to this accelerator?
Yeah, but you don't configure the cores. Like the cores are synthesized.
Okay, how do you say start?
Yes. Any way you want. Like what you get out of this is just a Verilog accelerator, like any other.
Okay, but the inputs, like which are going to be the inputs to start the acceleration, for example?
It depends on the interface that you ask for.
So I believe it can be data flow whenever the data is there available to just start something.
No, I think that would be that wouldn't work. So usually what you have is some control signals at the interface, and then the interface is towards external memory. So what you would do in the host application is you move the data to the memory where the FPGA will access that, and then you use some registers to set the control signals, and then the accelerator does everything else on its own.
Yeah, I think our questions are biased towards our research. So, yeah. We should talk it.
Yeah.
Yes.
So the idea is that we presented this as a kind of an architecture, but really it's one very long block. You don't get to go inside and disturb that, you know. Yeah.
If you have time, I have another question,
Yes.
or we can pass this next
Later
one.
because we have,
Yeah.
Later, okay.
or at the end because she has many things to show.
I think so. The last
Co-simulation.
big one is co-simulation. So one thing that we saw during doing HLS for all of these times and in many European projects was that the standard way of doing co-simulation to test the functionality of the accelerators we were generating was kind of cumbersome. You would have to just write a test bench, even maybe a C test bench, but still a dedicated function that would take inputs, fit them to the accelerator function, and then check them. And so this was extra manual work, and this means that if the kernel you're accelerating comes from a larger application, the functionality is not tested in the context of that application. It's something different. You have to maybe run the application and save data, and then take them and feed them to the accelerator in a different program. And then we thought that we can change this. So the framework that we have in place right now does something different. So it can take the whole application where the kernel to be accelerated was selected, and then uses the a process to run RTL simulation and a different process to run the host application. And what happens is that Bambu, together with generating the accelerator, it generates a lot of like glue logic and interfacing code to make this inter-process communication happen. And it replaces this kernel with a wrapper that controls the execution of the RTL simulation. It runs the software version of the same kernel, and then at the end, it automatically compares them. So the checking is done automatically. So if you launch the same kernels many times in the application with many different input data, it's basically painless to do the same tests on the generated hardware. Only thing, RTL simulation is slow. This is how it works with like a diagram of messages, but basically we use this inter-process communication, and we use the system-level direct programming interface, which allows something in this top-level function wrapper. It allows the C or C++ to communicate with the Verilog. We have accurate models for I/O protocols, and we estimate the memory latency because we don't have memory simulation here. Somehow this becomes faster than doing co-simulation in Vitis. I say somehow because co-simulation in Vitis is a black box. We don't know what it does, but we know it is slower. We've tested this, and it's under review at the moment. A lot of benefits. You get faster co-simulation in Vitis. You don't have to write a manual test bench every time that you do a new kernel, and you can just do more tests with realistic data. And another cool thing is, well, everything is auto-generated by Bambu. You don't have to touch anything in the Verilog test bench, verification logic. And because the top-level function wrapper replaced the original implementation, This means that you can also test that function in an application that's written in a different programming language. Why would you do that? Because, for example, we tried this with a weather simulation model that was accelerated with CUDA. With one of the kernels, we wrote it and synthesized it in Bambu. And to test that in the CUDA application, like, it's not like one file that you compile and write. It was a huge thing with a lot of make files. It was a complex application. So in this case, we could just take advantage of the fact that the interface of the generated wrapper is the same as the original function, and use this shared object preloading so that we could run the original application and it would not know that it was executing the wrapper instead of the original function. I'm not very good at explaining this, but it's a game changer. We can do this also in Python, because Python has C bindings. So if you have a Python application that dynamically loads a symbol, then you can replace that symbol with this wrapper function which runs the RTL simulation. And we did this with the ONNX runtime framework. So we just synthesized a neural network layer and then tested that in the context of the ONNX model. Okay.
Yeah.
Yeah.
I'm not sure if this could be useful for the verification team. It is just to do the co-simulation of a part that you are implementing in RTL and not the whole framework. I'm not sure if it's a usual use case, but
We would have to ask us.
okay. And we will ask of her.
And yeah, as I said, so there's some more work that we've done with co-simulation, but hopefully published soon, and then we'll talk about it. Just a few slides about what we're doing at the moment. I am working on a project that wants to accelerate some performance, like some modeling applications. This is an example of a modeling application modeling the spread of a disease in a population. Well, jumping through the math anyway, at the core of it, there is a set of ordinary differential equations. And we thought, okay, maybe we could solve these ODEs and apply both floating point customization and the multi-threading. So we did an example of it. We have an application that solves the N-body simulation with Runge-Tuta solver, and it plots something like that. And we can use TrueFloat to just take away bits and see how much we can get away with. And so, for example, when we get here, then we know we've cut too much. And the fact is that because of this new co-simulation framework, it was really easy to do this comparison because we used the same main program that was plotting the outputs, and we plugged the accelerator using the custom floating point formats in it, and we visually verify if the orbits still make sense. Then we have, well, the work with Gen 5. So I mentioned that our co-simulation method also sort of allows modeling host accelerator interfacing, but it would be better to have more of an architectural approach, and so we simulate the system as in like we simulate the processor and then all the connections and the accelerator. We'll see what we can do in these 2 weeks and beyond. And then we have potential work in these upcoming EU projects. Our goals for Bambu are to extend it to more ASIC backends and optimize it more for ASIC synthesis. Maybe we thought we can also take some feedback from the output of logic synthesis tools about timing and so on, and feed it back to Bambu to if there's some options that can be tuned to get a better result, and probably AI-guided design space exploration.
Are we gonna get tape out?
No, but then we will do it. So actually KNNL is doing a tape out, but the fact is that they had a slot on a foundry that then was bankrupt. I don't remember. Anyways.
No more chips.
Yes. Yeah. So I think they are kind of recovering that because someone else put the money. I don't know.
Yes, okay.
Not technical problems, you know.
So this is very relevant to us because we are also participating in all these projects.
Yeah,
So
exactly.
Teresa is there. She's coordinating on the digital stream, and then we have Oscar that couldn't make it today. He's in the productivity, and Pachi that is also here is the piano part. So that opens the door to this collaboration.
Yes, absolutely. Yeah. And just mandatory funding slides and the QR code that points us to the GitHub.
Good. So let's then the speaker. Okay, David, are you going to share those slides with us?
If you want to, yeah.
If possible, yes. I think you
Should I send it
you
to
have
you?
many things that could be interesting to other groups.